finally, the last model we'll consider is one in which the incoherent nature from second harmonic generation arises not from optical scatter per se, but from the generation of numerous sources of SHG that are phase incoherent. And a classic example of this is if you're imaging tissue, and you might have a lot of sources right at the top where the intensity of the fundamental light is quite high, but it's deep, but it's not focused. And then you have scattering losses, and then finally when you get down to the focal plane, you do definitely generate second harmonic generation from your sample, but there's also a lot of depolarized contributions from out of plane that sum incoherently with the SHG from your source. And that's going to not only increase your background, but it's also going to wreak havoc with the polarization analysis. So how do we then treat the contributions, the background contributions that can depolarize the second harmonic generation from numerous weak contributors out of plane? And if you think about it, this really starts to have a look and feel like a hyper-Rayleigh scattering experiment, because we've got lots and lots of weak contributors incoherently summing to generate the measured response. So we can build on the previous discussion we've had for hyper-Rayleigh scattering as a means of modeling this depolarized component to the SHG signal in this model. All right, so again, we've got this strong signal in the upward propagating direction, that's the coherent contribution, and then we have lots of tiny signals from incoherent contributions from additional sources that are out of plane. And we're going to treat this by hyper-Rayleigh scattering, assuming we have enough of these different orientations, or different crystals, that we sample a broad possible set of all possible orientations, each of which is roughly comparable in its intensity. So it does limit us to the assumption that there's a lot of tiny things that are contributing to the background. But in that limit, it gives us a handle for still how to treat it in terms of our known relationships based on hyper-Rayleigh scattering. So we can think of, in this limit, our total Mueller, this is in the vectorized notation, the total Mueller tensor is just going to be the Jones, the purely polarized component, times 1 minus alpha, plus the hyper-Rayleigh component times alpha. And the hyper-Rayleigh component we get from this expression by the orientational average over all possible Jones combinations, and then we just multiply, just like we would for the purely polarized component. That then gets propagated with this elementary matrix and through the set of A's to generate the Mueller, the set of indices in the Mueller tensor. Okay, and in fact we can group all of these things together and come up with something that, if we can actually keep it entirely in the Jones framework in terms of describing the purely polarized and the hyper-Rayleigh scattering contributions to the depolarization. So in vectorized form, this is what I had before. We can just group these together. Boy, I don't think the slide contributes anything from what was on the previous one, so we'll just move on. So the next step is clearly figuring out how to populate all these elements in the isotropic product for the Jones, for hyper-Rayleigh scattering. And we can build on the fact that we've done this already. We know how to handle all the hyper-Rayleigh scattering contributions for second harmonic generation. They boil down to these 4 unique independent tensor element combinations in the limit of either real valued tensor elements, or if everything is resonant with a particular interaction, all the tensor elements of identical phase. So these are described, the large majority of all measurements really boil down to just these 4 free parameters that are accessible in the Jones reference frame. And these are the 4 unique values. This is the full set of all of them. And they're broken up they're expressed in this binary notation where H is 0 and V is 1. So for example, this HVV combination, the the HVV is this one, and then the HVV there is for that one. And there's sort of a line in between here that separates the 3 indices and the corresponding ones in this 0 and 1 binary notation. And the advantage of relating it in terms of binary is that, hey, yeah, now we have a bookkeeping tool, because it's kind of a pain to keep track of all 64 of these things one at a time. So we can take advantage of binary counting to know which tensor elements correspond to which places in this Jones tensor product. And I'll show you how that plays out right here. If we've got 0, 1, 1, 0, 1, 1, and 1, 0, 0, 1, 0, 0 that are the 2 contributions from HVV, well, if we do binary counting of 0, 1, 1, 0, 1, 1, well, guess what? That turns out to be 27. So if I multiply this matrix, it's going to populate the 0, 1, 1, 0, 1, 1, the 27th element of this tensor product with 1 multiplied by HVV squared. And similarly, the 1, 0, 0, 1, 0, 0 corresponds to the binary number, corresponds to the decimal number of 36. So we can take advantage of the tensor orderings, the index orderings, to tell us the decimal location inside that symmetry matrix for the Jones transformation. So it's very easy to populate Q sub j based on knowledge of these 4 unique tensor elements. Okay. Now, that is writing everything in terms of the Jones reference frame, where we go back and fold alpha in to here. We actually don't have to yet. We can go back to this equation and instead consider this form where we don't fold everything in and consider instead 2 explicit contributions. One, the purely polarized component, and one, the purely depolarized component. But we keep them separate and keep them in the Mueller reference frame. And the reason for doing so is really up to you. Whatever you want to do. I'm just here to serve as a tool to help you get there. There are some times where it's more advantageous to not go through the Jones tensor notation, although those tend to be rare. But there are some times where it's more beneficial to describe it entirely in terms of the Mueller matrix formalism. And we can do that as well just as easily. If we think about this, for the purely polarized component, for the depolarized component, for the Mueller HRS, it's going to be given by, we don't need this, it's going to be given by everything else in this equation. And that's going to be all folded in to the symmetry matrix Q sub m. Well, we know that we can make the full population of things here for the Jones component using my Q sub j. And so if we want to generate Q sub m, well, all we do is we take the Q sub j, and this generates the full set of 27 elements for this ensemble averaged product of Jones tensor elements. And then if we do the elementary matrix to switch around the indices to put it into the Mueller reference frame and multiply it by the A's, then boom, we now have the corresponding symmetry matrix in the Mueller reference frame. And the numbers are different. There's some negative signs and some 1/2s in there because of the individual elements in A. But at 6 1/2 dozen of the other, it's very easy to go back and forth between the symmetry matrix that populates the full set of 64 elements in the hyper-Rayleigh scattering vector from the 4 unique non-zero elements, or the 64 elements in the product of the Jones tensor elements. So it's really straightforward to go back and forth between all of those. Now, if we want to consider how this plays out in terms of specific measurements, we will again consider polarization rotation measurements because they're fairly straightforward, and they also describe all the measurements you make with pure polarizations just by setting gamma, for example, in this case equal to 0, gives you horizontally polarized light, and gamma equal to 90 corresponds to vertically polarized light. And if we rotate gamma and measure all the different harmonics, we can back out 5 of them for the reasons that I'm going through this very quickly because this is all laid out in detail in the discussion of the Jones measurements and nose microscopy. And you end up with 5 parameters per detector, where n corresponds to either the horizontal detector or the vertical detector. And if we stack those on top of each other, then we have 5 for the horizontal on top of 5 for the 10, and we have 10 observables achievable from this polarization rotation measurement, and the corresponding values for in the limit of purely polarized contributions for the tensor element combinations responsible for those coefficients. So we can go ahead and describe these observables in terms of the purely polarized component and a purely unpolarized component. Then the question is, how do we make this alpha sub A, which is the vector of A elements, those vector of 10 coefficients that you would obtain in the limit of no polarization, or in the limit of hyper-Rayleigh scattering as the depolarized component. And again, it's actually really easy to do because we already have our Q matrix that populates the full set of chi j crossed chi j's. And so all we have to do is just plug that in using the symmetry properties of hyper-Rayleigh scattering to generate the A for that coefficient. And that's what you do. Yeah, I'm not sure where these came from, so we're just going to pretend these aren't here. How about that? But the rest of it's all well and good. This is, if you want to relate this back to the local frame tensor elements, then it's easy to do. You can basically subtract off this from your observables before you invert to solve for the local frame tensor elements. If you want to go all the way back to the molecular frame, it's the exact same idea. Subtract off the depolarized component first once you know alpha, and then you can determine beta, the molecular response, and or the orientation distribution from the remaining purely polarized component in your signal. If you want to do phase modulation, which we like to do because it's much faster than polarization rotation and therefore it results in a significant reduction in 1/f noise, the math is identical. In fact, the only thing that changes is the definition of P, which we haven't even gone through. But basically that's what connects the set of 10 observables back to the tensor element combinations. And here, because you're doing phase modulation, you end up with some complex valued terms and some negative terms in there that make P a little bit more interesting than they are in polarization rotation with just ones or zeros. But it's really just the only thing that changes is the definition of P, and nothing else in the analysis is affected by that difference in measurements. And so that gives us a good handle for inverting measurements and recovering local frame tensor elements from sets of observables recorded in the local frame and in the laboratory frame.